The ship of Theseus Paradox. Imagine you have a favorite old wooden ship. It's been in your family for generations, and it's named the ship of Theseus. Over the years, some of the wooden planks start to rot. So, you replace them. At first, it's just a few planks here and there. But as more time passes, more and more planks need replacing. Eventually, you've replaced every single plank, every sail, every bit of rope on the ship. The question is this still the ship of Theseus? On one hand, you could argue that of course it is. You never at any point bought a new ship. You just repaired the one you had. It's been a continuous process of maintenance. From a practical standpoint, it's the same vessel that has been docked in the same harbor, the one you've always pointed to and said, that's the ship of Theseus. But on the other hand, not a single physical piece of the original ship remains. If you had saved all the old, rotten planks you removed and then, as a side project, reassembled them, which one would be the real ship of Theseus? The one made of all the new materials, or the one made of all the original, albeit decayed, parts? This is a puzzle that the philosopher Thomas Hobbes added to the original paradox. This thought experiment, first recorded by the ancient Greek historian Plutarch, gets at the heart of what makes something itself. Is an object defined by its physical components, or by its history and the continuity of its existence? It's not just about ships. Think about your own body. Most of the cells in your body are replaced over time. Are you the same person you were 7 years ago? The vast majority of your body's cells are renewed periodically, with around 330 billion cells being replaced each day. This paradox forces us to question what identity truly means. Is it in the physical stuff we're made of, or is it something more abstract, like our memories, our personality, or in the case of the ship, its form and function? The Grandfather Paradox. Imagine you've built a time machine. You decide to go back in time to when your grandfather was a young man, long before he met your grandmother. For some reason, you decide to kill him. Now, if you kill your grandfather, he can't have children. That means your parents were never born. And if your parents are never born, then you are never born. But if you were never born, how could you have gone back in time to kill your grandfather in the first place? This creates a major contradiction. Your action in the past prevents your own existence, which in turn means you couldn't have performed that action. It's a loop of impossibility. This paradox is often used as an argument against the very possibility of traveling to the past. Some interpretations suggest that any change to the past is impossible because it would lead to a logical contradiction. So, how do science fiction and theoretical physics try to solve this? One idea is the self-consistency principle. This theory suggests that the universe has a way of protecting itself from paradoxes. No matter what you do in the past, you can't change it in a way that creates a contradiction. So, if you went back to kill your grandfather, something would always prevent you. Maybe you'd slip on a banana peel, or your weapon would jam. Essentially, you're destined to fail. Another popular solution is the idea of multiple timelines or parallel universes. When you travel back in time and kill your grandfather, you've created a new timeline. In this new timeline, you were never born. But in your original timeline, your grandfather lived, and you were born, and you built a time machine. So, both timelines exist, but they are separate realities. This neatly avoids the paradox by saying that your actions in the past create a new branch of reality, but they don't erase the reality you came from. Then there's the idea that your actions in the past were always a part of history. You going back in time to change something was actually the event that caused the future you know. This leads us right into our next paradox. The Bootstrap Paradox. This one is a real mind-bender. The Bootstrap Paradox, also known as a causal loop, happens when an object or a piece of information has no clear origin. Imagine this: a time traveler is a huge fan of a famous composer. He travels back in time to meet his idol, bringing with him a copy of the composer's most brilliant symphony. But when he gets there, he finds out the composer hasn't written it yet. In a moment of inspiration, the time traveler gives the sheet music to the composer, who then publishes it as his own. The symphony becomes famous, and centuries later, the time traveler is born, hears the music, and is so inspired that he decides to go back in time to meet the composer, bringing the sheet music with him. So, the question is, who wrote the symphony? The composer didn't, he got it from the time traveler. But the time traveler didn't write it either, he just copied it from the composer's famous work. It seems the symphony has no origin. It's caught in an endless loop, existing without ever being created. This is the essence of the Bootstrap Paradox. It gets its name from the phrase, to pull oneself up by one's bootstraps, which describes an impossible action. This paradox challenges our fundamental understanding of cause and effect. We're used to a linear progression of events, a cause is B, which causes C. But in a bootstrap paradox, the future can influence the past, and an event can essentially be its own cause. It's a self-contained loop with no beginning and no end. Science fiction loves this one. Think about a character receiving a piece of future technology from their future self, which then allows them to invent that very technology. The technology exists, but it was never truly invented. It just is. This paradox suggests a universe where time is not a straight line, but can be a circle, with events endlessly repeating and reinforcing each other. The Fermi Paradox. Let's look up at the night sky. Our galaxy, the Milky Way, has hundreds of billions of stars. And we now know that most of those stars have planets orbiting them. Statistically speaking, a significant number of those planets should be in the habitable zone, where conditions are right for liquid water to exist. If even a tiny fraction of those planets developed life, and an even tinier fraction of that life became intelligent and developed technology, our galaxy would be teeming with civilizations. So, here's the paradox, famously posed by physicist Enrico Fermi: if the odds of alien life are so high, where is everybody? This is the Fermi Paradox. It's the stark contradiction between the high probability of extraterrestrial intelligence and the complete lack of evidence for it. There are many possible solutions to this puzzle, some more optimistic than others. One possibility is that intelligent life is incredibly rare. Maybe the jump from simple life to complex, intelligent beings is a huge hurdle that almost never happens. This is sometimes called the Great Filter theory. It suggests there's some evolutionary or technological barrier that is extremely difficult for life to overcome, and humanity may be one of the very few, or even the only, species to have made it through. Another, more sobering, possibility is that intelligent civilizations don't last very long. Perhaps they inevitably destroy themselves through war, climate change, or some other self-inflicted catastrophe. If the lifespan of a technological civilization is short, then the chances of two of them existing at the same time in the same galactic neighborhood are slim. Of course, there are other, less grim, possibilities. Maybe they are out there, but they're just too far away for us to detect. Space is vast, and the signals we're looking for might be too weak to reach us. Or perhaps they are intentionally staying silent, not wanting to attract unwanted attention. It's also possible that their technology is so advanced that we wouldn't even recognize their signals. They could be communicating in ways we can't even imagine. Or, perhaps the most humbling thought of all, maybe they've been here and we just haven't noticed. Zeno's paradoxes. Imagine you want to walk to a wall. To get there, you first have to walk half the distance. Once you're halfway, you still have to walk half of the remaining distance. And once you've done that, you have to walk half of what's left, and so on. You can keep dividing the remaining distance in half an infinite number of times. So, how do you ever actually reach the wall? This is one of the famous paradoxes of the ancient Greek philosopher Zeno of Elea. He came up with several of these thought experiments to argue that motion is just an illusion. Another well-known one is the Achilles and the Tortoise Paradox. The swift runner Achilles is in a race with a tortoise, and he gives the tortoise a head start. To catch the tortoise, Achilles must first reach the point where the tortoise started. But by the time he gets there, the tortoise has moved a little further ahead. So, Achilles must then reach that new spot. But by the time he does, the tortoise has moved on again. This process can be repeated infinitely, so it seems Achilles can never catch the tortoise. Of course, we know in the real world that you can walk to a wall and that a fast runner can overtake a slow one. So, what's going on here? Zeno's paradoxes highlight the tricky nature of infinity. The solution to these puzzles lies in a branch of mathematics that wasn't fully developed until long after Zeno's time, calculus. The key is that an infinite number of smaller and smaller distances can still add up to a finite total distance. As you get closer to the wall, the halfway points you're crossing become infinitesimally small, and the time it takes to cross them also becomes infinitesimally small. So, even though there are an infinite number of steps, you can complete them in a finite amount of time. Zeno's paradoxes were incredibly influential in the development of mathematics and philosophy. They forced people to think deeply about concepts like infinity, space, and time in ways they never had before. And even though we now have the mathematical tools to resolve them, they still serve as a great reminder that our intuitive understanding of the world can sometimes be misleading. The Sorites Paradox, heap paradox. Imagine a single grain of sand. Is that a heap of sand? Of course not. Now, add another grain. Is that a heap? Still no. If you keep adding one grain of sand at a time, at what exact point does it become a heap? Can a single grain of sand be the one that makes the difference between not a heap and a heap? This is the Sorites Paradox, also known as the Paradox of the Heap. It arises because we use vague terms like heap, bald, or tall that don't have a precise, clear-cut definition. The paradox works by starting with a clear case of something not being a heap and then making tiny, incremental changes. Each individual change seems to make no difference, but eventually, you end up with a clear case of a heap. The paradox is that there's no logical place to draw the line. You can run the paradox in the other direction too. Start with a massive heap of sand. If you remove one grain, it's still a heap. If you remove another, it's still a heap. If you keep removing one grain at a time, you'll eventually be left with just one grain, which is clearly not a heap. So, when did it stop being a heap? This paradox highlights a problem with how our language and logic deal with vague concepts. In classical logic, a statement is either true or false. You are either bald or not bald. Something is either a heap or it is not. But in the real world, things are often not so black and white. There are gray areas. Philosophers have proposed various ways to deal with this paradox. Some have suggested that there is a sharp line, we just don't know where it is. Others have proposed new systems of logic, like fuzzy logic, which allows for degrees of truth. In fuzzy logic, something could be 0.7 heap or 0.2 bald. This allows for the gradual transition from one state to another that we see in the real world. The Sorites Paradox shows us that while our everyday language is incredibly useful, it can also lead to some perplexing logical puzzles when we try to apply strict rules to it. The Barber Paradox. Imagine a town with a single barber. This barber has a very specific rule: he shaves all the men in town who do not shave themselves, and only those men. So, if a man in the town doesn't shave himself, the barber shaves him. If a man does shave himself, the barber doesn't. Simple enough, right? Now, here's the question: who shaves the barber? Let's think it through. If the barber shaves himself, then he is one of the men who shaves himself. But according to his own rule, he doesn't shave men who shave themselves. So, if he shaves himself, he can't shave himself. That's a contradiction. Okay, so let's say the barber does not shave himself. Well, according to his rule, he shaves all the men who do not shave themselves. Since he is a man in the town who doesn't shave himself, he must be shaved by the barber. So, if he doesn't shave himself, he must shave himself. Another contradiction. We're stuck. No matter which option we choose, we end up with a logical impossibility. The barber both shaves himself and doesn't shave himself. This is the Barber Paradox. It's a puzzle that was used by the philosopher Bertrand Russell to illustrate a deeper problem in a field of mathematics called set theory. The paradox shows that an apparently plausible scenario can be logically impossible. The problem lies in the way the barber's rule is defined. It's a self-referential rule that creates a situation that can't be resolved. The conclusion that most logicians come to is simply that such a barber cannot exist. The very definition of this barber is self-contradictory, so the whole scenario is impossible from the start. It's a neat little puzzle that demonstrates how easily our language can tie itself in logical knots. The Omnipotence Paradox. This is a classic theological and philosophical puzzle that questions the very nature of unlimited power. The most common version of the Omnipotence Paradox is this: can an all-powerful being create a stone so heavy that even they cannot lift it? Let's break down the dilemma. If the being can create a stone they cannot lift, then there's something they can't do: lift the stone. This means they are not all-powerful. On the other hand, if the being cannot create a stone they cannot lift, then there's something they can't do: create the stone. This also means they are not all-powerful. Either way, it seems the idea of omnipotence is self-contradictory. So, how have thinkers tried to resolve this? One common response is to refine the definition of omnipotence. Many philosophers and theologians argue that being all-powerful doesn't mean you can do things that are logically impossible. For example, an omnipotent being can't create a square circle or a married bachelor. These things aren't things at all, they are just contradictory combinations of words. In this view, creating a stone that an all-powerful being cannot lift is also a logical contradiction. It's like asking if an irresistible force can move an immovable object. The two concepts are mutually exclusive. Another way to look at it is that an omnipotent being exists outside the laws of logic that bind us. If this is the case, then the question itself is flawed because it's trying to apply human logic to a being that is not bound by it. From this perspective, the answer could be yes and no, or something else that our minds simply can't comprehend. The Omnipotence Paradox is a powerful tool for exploring the limits of logic and language. It forces us to think carefully about what we mean by concepts like power and possibility. Whether you see it as a clever word game or a profound theological problem, it's a paradox that has fascinated and challenged thinkers for centuries. The Liar's Paradox. This is a very old and very famous paradox that gets right to the heart of truth and self-reference. In its simplest form, the Liar's Paradox is the sentence, "This statement is false." Now, let's try to figure out if that sentence is true or false. If the sentence is true, then what it says must be true. And what it says is that the sentence is false. So, if it's true, it must be false. That's a contradiction. Okay, so let's assume the sentence is false. If it's false, then what it says is not true. It says the sentence is false, and if that's not true, it means the sentence must be true. So, if it's false, it must be true. Another contradiction. We're trapped in a logical loop. The sentence seems to be both true and false, and also neither true nor false. This little sentence seems to break the fundamental rules of logic. This paradox has been around for over 2,000 years and has been a headache for logicians and philosophers ever since. There have been many attempts to solve it. One idea is that the sentence is simply meaningless. It looks like a proper sentence, but because it's self-referential in this particular way, it doesn't actually express a meaningful proposition. It's just a string of words that doesn't have a truth value. Another approach, proposed by the logician Alfred Tarski, is that we need to be very careful about the language we use to talk about truth. He suggested that we should distinguish between an object language and a metalanguage. The object language is the language we're talking about, and the metalanguage is the language we're using to talk about it. According to Tarski, a sentence in a language can't talk about its own truth value. So, this statement is false, is a grammatically flawed sentence because it's trying to do something that language isn't equipped to do. The liar's paradox is more than just a brain teaser. It has had a huge impact on logic and the philosophy of language, and it's related to some very deep results in mathematics, like Gödel's incompleteness theorems. It shows that even in the most rigorous systems of thought, we can still run into surprising and profound puzzles. The paradox of tolerance. This is a paradox that has become increasingly relevant in modern discussions about politics and society. The paradox of tolerance was first described by the philosopher Karl Popper. He argued that in order to maintain a tolerant society, that society must be intolerant of intolerance. At first, that sounds like a contradiction. How can you be tolerant if you're being intolerant? But Popper's point was this: if a tolerant society extends unlimited tolerance to those who are intolerant, the intolerant will eventually destroy the tolerant, and tolerance with them. Imagine a society that values open-mindedness and free speech above all else. Now, imagine a group within that society that advocates for the suppression of free speech and the persecution of minorities. If the tolerant society tolerates this group, allowing them to spread their ideas and gain power, that intolerant group could eventually take over and create a society where there is no tolerance at all. So, according to Popper, a tolerant society has the right, and even the duty, to defend itself against those who would destroy it. This doesn't mean we should suppress all intolerant ideas from the very beginning. Popper believed we should first try to counter them with rational argument and public opinion. But if that fails, and the intolerant group starts to become a real threat to the foundations of the tolerant society, then the tolerant society must be prepared to be intolerant of them. The paradox lies in the question of where to draw the line. How do we decide which ideas are so intolerant that they can no longer be tolerated? If we're not careful, the argument for being intolerant of intolerance can be used to justify suppressing any idea we don't like. The paradox of tolerance is a tricky ethical and political problem with no easy answers. It forces us to think about the limits of tolerance and what we're willing to do to protect a free and open society. It's a reminder that sometimes, the principles we hold dear can have complex and even contradictory implications. The unexpected hanging paradox. A judge sentences a prisoner to be hanged at noon on one of the next 5 weekdays, from Monday to Friday. He tells the prisoner two things: first, the hanging will definitely happen on one of those 5 days. Second, it will be a surprise. The prisoner will not know the day of the hanging until the executioner arrives at his cell at noon. The prisoner, a keen logician, thinks about this and comes to a startling conclusion: he cannot be hanged. Here's his reasoning. He starts by thinking about the last possible day, Friday. The hanging can't be on Friday, he says to himself. If I'm still alive on Thursday afternoon, I'll know for sure that the hanging must be on Friday. But the judge said it would be a surprise. So, Friday is out. Having eliminated Friday, he then considers Thursday. Well, since Friday is no longer a possibility, Thursday is now the last possible day. If I'm still here on Wednesday afternoon, I'll know the hanging has to be on Thursday. That wouldn't be a surprise either. So, Thursday is also out. He continues this backward logic, eliminating Wednesday, then Tuesday, and finally Monday. He's left with no possible day for the hanging to occur. He feels a sense of relief, confident that the judge's sentence is self-contradictory and therefore cannot be carried out. And then, on Wednesday at noon, the executioner knocks on his door. The prisoner is completely and utterly surprised. The judge's words came true after all. So what went wrong with the prisoner's logic? It seems perfectly sound, step by step. This paradox plays with our understanding of knowledge, expectation, and self-reference. The core of the problem lies in the prisoner's assumption that he can know the judge's statements to be true and use them to predict the future. The judge's statement that the hanging will be a surprise is a self-referential statement. The moment the prisoner uses it to make a deduction, he changes his own state of knowledge, which can affect the truth of the statement itself. The paradox forces us to question whether it's possible for someone to have complete knowledge of a set of rules when one of those rules is about their own lack of knowledge. The Raven Paradox. Let's say you're a budding ornithologist, and you have a hypothesis: all ravens are black. To test this, you go out and observe ravens. Every time you see a black raven, it provides a little bit of evidence to support your hypothesis. This is the foundation of inductive reasoning. We make general rules based on specific observations. Now, here's where it gets weird. The statement, all ravens are black, is logically equivalent to the statement, everything that is not black is not a raven. Think about it: if all ravens are black, then anything that isn't black can't possibly be a raven. The two statements mean the exact same thing. So, if observing a black raven supports the first statement, then observing something that confirms the second statement should also support the first one. This leads to a strange conclusion. If you look at a green apple, it is not black, and it is not a raven. Therefore, it confirms the statement, everything that is not black is not a raven. And since that statement is logically the same as, all ravens are black, observing a green apple, a red bus, or a yellow post-it note should, in a strictly logical sense, increase your confidence that all ravens are black. This feels completely wrong. How can looking at things in your office provide evidence about the color of birds you've never seen? This is the Raven Paradox, also known as Hempel's Paradox. It doesn't necessarily mean our system of logic is broken, but it does highlight the difference between strict logical confirmation and what we intuitively consider to be meaningful evidence. One of the most common resolutions to this paradox is that while observing a green apple does technically provide evidence, the amount of evidence is infinitesimally small. 5. There are vastly more non-black things in the universe than there are ravens. So, seeing one more non-black, non-raven object barely changes the probability that your hypothesis is true. On the other hand, finding a new black raven is a much more significant piece of evidence because the number of ravens is much smaller. The paradox shows us that not all evidence is created equal. The Monty Paradox. Imagine you're on a game show. The host, Monty Hall, shows you 3 doors. Behind one door is a brand new car, and behind the other 2 are goats. You get to pick one door. Let's say you pick door number 1. You don't know what's behind it yet. Now, Monty, who knows where the car is, does something interesting. He opens one of the other 2 doors, say door number 3, to reveal a goat. He then gives you a choice: do you want to stick with your original choice, door number 1, or do you want to switch to the other unopened door, door number 2? Most people's intuition says it doesn't matter. There are 2 doors left, so it must be a 50-50th chance. But that intuition is wrong. You should always switch. Switching doors doubles your chances of winning the car. Here's why. When you first picked a door, you had a 1 in 3 chance of picking the car and a 2 in 3 chance of picking a goat. That means there's a 2/3 probability that the car is behind one of the doors you didn't pick. When Monty opens one of the other doors to show you a goat, he's giving you new information. He's not just opening a random door, he's specifically opening a door that he knows has a goat. If you initially picked a goat, which happens 2/3 of the time, Monty has to open the other goat door. That means the remaining unopened door must have the car. So, if you switch, you win. If you initially picked the car, which happens 1/3 of the time, Monty will open one of the 2 goat doors. In this case, if you switch, you lose. So, by switching, you win if your initial pick was a goat, a 2/3 probability, and you lose if your initial pick was the car, a 1/3 probability. Your chances of winning by switching are 2 out of 3. It's a tricky problem because our brains tend to reset the odds to 50-50 once there are only 2 options left, but we forget to account for the crucial information that Monty gives us with his deliberate action. The 2 envelopes paradox. Here's a puzzle that can make you question your understanding of probability and expected value. Imagine someone presents you with 2 sealed envelopes. They tell you that one envelope contains twice as much money as the other, but you don't know which is which. You are allowed to pick one envelope. You pick one, but before you open it, you're given the chance to switch to the other envelope. Should you switch? Let's try to reason this out with some math. Let's say the amount of money in your chosen envelope is X. Then the other envelope has either 2X, if you chose the smaller amount, or X/2, if you chose the larger amount. You don't know which case you're in, so you might assume there's a 50% chance of each. So, let's calculate the expected value of switching. There's a 0.5 probability the other envelope has 2X, and a 0.5 probability it has X/2. The expected value would be 0.5*2x plus 0.5*x/2, which simplifies to x plus x/4, or 1.25x. This calculation suggests that, on average, the other envelope contains more money than the one you're holding. So, it seems like you should always switch. But here's the paradox: the situation is perfectly symmetrical. If you had chosen the other envelope first, the exact same logic would tell you to switch back to the one you're currently holding. It can't be correct that it's always better to switch, no matter which envelope you have. So, what's wrong with the calculation? The flaw is a bit subtle. It lies in how we're using the variable x. When we do the calculation, we're treating x as a fixed amount. But the value of x is different in the two scenarios. If your envelope has the smaller amount, let's call it s, then x equals s, and the other envelope has 2s. If your envelope has the larger amount, 2s, then x equals 2s, and the other envelope has s. The x in the 2x part of the calculation represents a different amount than the x in the x/2 part. You can't just average them out in that simple way. The paradox is a good lesson in being careful about what your variables represent in a probability problem. The lottery paradox. Imagine a fair lottery with 1,000 tickets, and you know for a fact that there will be exactly one winner. Now, consider any single ticket, say ticket number 1. The probability of this ticket winning is 1 in 1,000, or 0.1%. The probability of it not winning is 99.9%. That's a very high probability. It seems perfectly reasonable to believe that ticket number 1 will not win. Since the lottery is fair, the same logic applies to ticket number 2. It has a 99.9% chance of not winning, so it's rational to believe that ticket number 2 will not win. You can continue this for every single ticket in the lottery. For any individual ticket, it is highly probable that it will not be the winner, so it's rational to believe it won't win. But now we have a problem. If you believe that ticket number 1 won't win, and you believe that ticket number 2 won't win, and so on for all 1,000 tickets, then you should also believe that no ticket will win. But you know for a fact that one ticket must win. So you now hold a set of beliefs that are individually rational, but collectively contradictory. You believe that no ticket will win, and at the same time, you believe that one ticket will win. This is the lottery paradox. It highlights a conflict between what seems rational to believe about individual events and what we know must be true about the collection of those events. It challenges the idea that if we are justified in believing a set of individual statements, we are also justified in believing their logical consequences. This paradox has led philosophers to think deeply about the nature of belief, knowledge, and probability. Some argue that you shouldn't claim to know that your ticket will lose, even if it's overwhelmingly likely. You should only believe that it is very likely to lose. The paradox shows that there's a tricky relationship between high probability and outright belief, and that our everyday reasoning about probability can sometimes lead us into logical traps. The Sleeping Beauty Paradox. This is a thought experiment in probability and self-locating belief that has philosophers and mathematicians fiercely debating. Here's the setup. On Sunday, researchers tell Sleeping Beauty the plan. They are going to put her to sleep, and then they will toss a fair coin. If the coin comes up heads, they will wake her up on Monday for an interview, and then the experiment is over. If the coin comes up tails, they will wake her up on Monday for an interview, then give her a drug that makes her forget being woken up, and then wake her up again on Tuesday for another interview. So, every time she wakes up, she won't know if it's Monday or Tuesday, and she won't remember any previous awakenings. She knows all of these rules. The question is, when she is awakened and interviewed, what should her degree of belief be that the coin landed on heads? There are two main schools of thought. The halfers argue that the answer is 1/2. Their reasoning is that Sleeping Beauty knew the coin was fair on Sunday, and when she wakes up, she doesn't gain any new information that should change her belief. The outcome of the coin toss is independent of how many times she is awakened. The fundamental probability of a fair coin toss is 50-50, and that shouldn't change. The thirders argue that the answer is 1/3. They look at the situation from the perspective of all possible awakenings. Over many repetitions of this experiment, there will be, on average, 1 heads awakening for every 2 tails awakenings. So, out of every 3 awakenings, 1 will be a heads awakening and 2 will be tails awakenings. Therefore, when she finds herself awake, she should believe there is a 1 in 3 chance that it's a heads awakening. This paradox is so tricky because it pits our intuitions about classical probability against a situation where the number of times an observer makes an observation is itself dependent on the outcome of the random event. It forces us to ask what it means to calculate a probability from a first-person perspective when that perspective might be duplicated. The paradox of choice. We live in a world that celebrates choice. The more options we have, the better, right? More choice means more freedom, and more freedom means more well-being. But the psychologist Barry Schwartz argues that this isn't always the case. He calls this the paradox of choice. The idea is that while some choice is good, an overabundance of choice can actually be detrimental to our psychological and emotional well-being. Here's how it works. When we're faced with a huge number of options, say, picking a jam from a supermarket shelf with 200 varieties, or choosing a career path from an endless list of possibilities, a few negative things can happen. First, it can lead to analysis paralysis. The sheer volume of choices can be overwhelming, and we can end up so worried about making the wrong choice that we don't make any choice at all. Second, even if we do make a choice, we're often less satisfied with it than if we had fewer options to begin with. This is because with so many alternatives, it's easy to imagine that we could have made a better choice. We start to think about the features of the options we didn't choose, and this can lead to regret and a feeling of missed opportunities. Third, an excess of choice can lead to an escalation of expectations. When there are only a few options, we might be happy to find one that's pretty good. But when there are hundreds of options, we expect to find the perfect one. This can set us up for disappointment, because even a very good choice might not live up to our now sky-high expectations. The paradox is that by trying to maximize our freedom and satisfaction by having more choices, we can end up feeling more paralyzed, more anxious, and less happy with what we have. Schwartz suggests that the key to overcoming this is not to eliminate choice, but to be more mindful about it, to learn to accept good enough instead of always striving for the absolute best, and to focus on the choices that truly matter. The Paradox of Hedonism. The Paradox of Hedonism, also known as the Pleasure Paradox, is the observation that the direct pursuit of pleasure is often self-defeating. In other words, the more you actively seek out happiness and pleasure, the more it seems to elude you. Conversely, happiness often comes as an unintended side effect of engaging in other activities. Think about it this way. If you make your sole goal in life to be happy, you're likely to be constantly evaluating your emotional state, asking yourself, am I happy now? How about now? This constant self-monitoring can actually interfere with the experience of genuine happiness. It's like trying to fall asleep by constantly thinking about falling asleep. It usually doesn't work. The paradox suggests that happiness and pleasure are not things that can be pursued directly. They are byproducts. People often find the greatest joy and satisfaction when they are absorbed in a challenging task, pursuing a meaningful goal, or dedicating themselves to a cause greater than themselves. The pleasure comes from the activity itself, not from a conscious effort to extract pleasure from it. The philosopher John Stuart Mill, who was a proponent of a form of hedonism called utilitarianism, experienced this paradox firsthand. He realized that those who are happiest are those who have their minds fixed on some object other than their own happiness, on the happiness of others, on the improvement of mankind, even on some art or pursuit, followed not as a means, but as itself an ideal end. By aiming at something else, they find happiness by the way. This is the heart of the paradox: to get pleasure, you have to forget about it. The Paradox of Thrift. Here's a paradox from the world of economics that seems to go against our common sense about saving money. On an individual level, saving is a virtue. If you save more of your income, you'll be better off financially. But the paradox of thrift, popularized by the economist John Maynard Keynes, suggests that if everyone in an economy tries to save more at the same time, it can actually make everyone poorer. Here's the logic. In a modern economy, one person's spending is another person's income. If you decide to save more, that means you're spending less. If everyone starts spending less, then businesses will see their sales decline. In response to this drop in demand, they'll likely cut back on production and lay off workers. This creates a vicious cycle. As more people lose their jobs, the total income of the country goes down. And when people's incomes are lower, they are able to save less, even if they want to. So, the collective attempt to increase savings ends up reducing the total income of the economy, which in turn can lead to a decrease in the total amount of savings. This paradox is particularly relevant during an economic recession. When times are tough, it's natural for individuals to want to cut back on spending and save more. But if everyone does this at once, it can deepen the recession. This is why Keynesian economics often advocates for government spending during a downturn to make up for the lack of consumer spending and to break the cycle of the paradox of thrift. It's a powerful reminder that what makes sense for an individual doesn't always make sense for the economy as a whole. The Friendship Paradox. Here's a curious and mathematically provable fact about social networks: on average, your friends have more friends than you do. This might sound like a downer, but it's a statistical reality known as the Friendship Paradox. It's not about you personally. It's a result of a sampling bias in how we experience social networks. People who have a very large number of friends are, by their very nature, more likely to be one of your friends. They are overrepresented in the friend groups of others. Think of it this way: someone with 1,000 friends is a part of 1,000 different friend circles, while someone with only one friend is only a part of one. So, you're much more likely to be friends with the super-connected person. Because these highly popular people show up in so many friend groups, they pull up the average number of friends of your friends. Meanwhile, people with very few friends are less likely to be in your social circle to begin with. This skews the average. This paradox isn't just about the number of friends. A generalized friendship paradox shows that the same principle applies to other characteristics. For example, your co-authors on a paper are likely to have more publications than you, and the people you follow on social media are likely to have more followers than you. The Friendship Paradox is a great example of how our intuitive understanding of averages can be misled by the structure of networks. It has some interesting practical applications, too. For instance, public health officials can use this principle to help track and prevent the spread of diseases. By identifying the friends of randomly selected people, they can find individuals who are more centrally located in the social network and are therefore more likely to be exposed to and spread an illness. The Jevons Paradox. Here's a puzzle that seems to defy a basic principle of environmentalism. We tend to think that if we make our technology more efficient, we'll use less of the resource that technology relies on. For example, if you invent a car that gets double the gas mileage, you'd expect gasoline consumption to go down. But the Jevons Paradox, first observed by the English economist William Stanley Jevons in the 19th century, says that the opposite often happens. Jevons was studying coal consumption during the Industrial Revolution. He noticed that as steam engines became more efficient, using less coal to produce the same amount of power, the total amount of coal being consumed in England actually skyrocketed. This seemed completely backward. How could a more efficient engine lead to more coal use? The answer lies in economics and human behavior. When a technology becomes more efficient, it effectively makes the resource cheaper to use. A more efficient steam engine meant that the cost of power went down. This had two effects. First, people could now afford to use their steam engines more. A factory owner might decide to run his machinery for longer hours because the fuel cost was lower. Second, and more importantly, the newfound efficiency and lower cost opened up entirely new applications for the technology. Suddenly, it became economically viable to use steam engines in places where they were previously too expensive, like in smaller factories or for new types of machinery. So, while the efficiency of each individual engine went up, the number of engines and their uses expanded so dramatically that the overall consumption of coal increased. We see this today with many technologies. More fuel-efficient cars can lead people to drive more or to buy larger, heavier vehicles, offsetting some of the gains. More energy-efficient lighting can lead people to light up more areas or leave lights on for longer. The Jevons Paradox is a crucial concept in environmental economics. It doesn't mean that we shouldn't strive for energy efficiency. Efficiency is still a good thing as it allows us to get more value from our resources. But it does serve as a powerful reminder that efficiency alone is not a silver bullet for sustainability. We also have to consider the rebound effects and the overall scale of our consumption. The paradox of value, diamond, water paradox. Let's think about two things, water and diamonds. Which one is more valuable? On the one hand, water is essential for life. Without it, we would die in a matter of days. Diamonds, on the other hand, are mostly just shiny rocks. They have some industrial uses, but for the most part, they are a luxury item with no practical survival benefit. So, water should be far more valuable than diamonds, right? But then, look at the market price. A small diamond can cost thousands of dollars, while a bottle of water costs next to nothing. This is the paradox of value, a puzzle that stumped early economists like Adam Smith. Why is something so essential, like water, so cheap, while something so non-essential, like diamonds, is so expensive? The solution to this paradox lies in the concepts of scarcity and marginal utility. The key is to not think about the total usefulness of water versus the total usefulness of diamonds, but to think about the usefulness of the next unit of water or diamonds. Water is incredibly abundant. There is so much of it that the next glass of water you drink has a relatively low value to you. You've already had plenty to drink, so one more glass isn't a big deal. This is what economists call low marginal utility. Because water is so plentiful, its price is low. Diamonds, however, are extremely rare. Because they are so scarce, the marginal utility of one more diamond is very high. For most people, who have 0 diamonds, getting just one would be a significant increase in their perceived wealth and status. Because the supply is so limited and the desire for them is high, people are willing to pay a much higher price. So, the paradox is resolved by understanding that price is not determined by the total usefulness of a good, but by its scarcity and the value we place on having one additional unit of it. If you were stranded in the desert, dying of thirst, the marginal utility of a glass of water would be infinitely high, and you would likely trade a whole handful of diamonds for it. In that context, the paradox disappears entirely. The Abilene Paradox. Imagine a family, a husband, a wife, and her parents, sitting on a porch in Coleman, Texas, on a hot and dusty afternoon. It's a boring day. The father-in-law suggests, "Hey, why don't we drive to Abilene for dinner?" Abilene is over 50 miles away, a long, hot drive in a car with no air conditioning. The wife thinks it's a terrible idea, but she looks at her husband and figures he might want to go, so she says, "Sounds good to me." The husband also thinks it's a foolish idea, but he doesn't want to rock the boat, and he assumes his in-laws are keen on it, so he says, "Sure, I'm game." The mother-in-law, who would much rather stay home, agrees as well because she doesn't want to be a spoilsport. So, the four of them get in the car and endure a miserable, dusty, 4-hour round trip to a mediocre cafeteria in Abilene. When they get back, exhausted and irritable, someone finally admits, "That was a terrible idea. I never wanted to go." And then, one by one, the others confess that they didn't want to go either. They only went because they thought everyone else wanted to. This is the Abilene Paradox, a term coined by management expert Jerry B. Harvey. It describes a situation where a group of people collectively decides on a course of action that is counter to the preferences of any of the individuals in the group. It's not a case of one person giving in to the group, it's a situation where everyone is giving in to what they think the group wants, leading to a decision that nobody actually supports. The core of the paradox is the inability to manage agreement, not disagreement. It happens because of a breakdown in communication and a fear of social consequences. People don't want to be seen as disagreeable or to challenge the perceived consensus. This can happen in business meetings, in government, and in our personal lives. It leads to bad decisions, wasted resources, and a lot of frustration. The key to avoiding the Abilene Paradox is to create an environment where people feel safe to voice their true opinions and to question the assumptions about what the group really wants. Galileo's Paradox of Infinity. Let's take a look at the set of all natural numbers, 1, 2, 3, 4, 5, and so on. It's an infinite set. Now, let's look at the set of all square numbers, 1, 4, 9, 16, 25, and so on. This is also an infinite set. The paradox, as pointed out by Galileo Galilei in the 17th century, arises when we try to compare the size of these two infinite sets. On the one hand, it seems obvious that there must be more natural numbers than square numbers. After all, the square numbers are a subset of the natural numbers. For every square number, there's a corresponding natural number, but there are lots of natural numbers, like 2, 3, 5, 6, that are not squares. So, the set of natural numbers should be bigger. But on the other hand, Galileo noticed something strange. You can create a perfect one-to-one correspondence between the natural numbers and the square numbers. For every natural number, n, there is exactly one square number n superscript 2. For 1, there's 1. For 2, there's 4. For 3, there's 9, and so on. You can go on forever, and you will never run out of numbers in either list. Since you can match them up perfectly, one to one, it seems like the two sets must be the same size. So, which is it? Is the set of natural numbers bigger than the set of square numbers, or are they the same size? This is Galileo's paradox. It stumped mathematicians for centuries because it showed that our finite intuition about size and quantity breaks down when we try to apply it to infinity. The rules that work for finite sets, like the idea that a whole must be greater than its parts, don't necessarily work for infinite sets. The modern resolution to this paradox came in the late 19th century with the work of George Cantor, the founder of modern set theory. Cantor defined the size of an infinite set, its cardinality, by its ability to be put into a one-to-one correspondence with another set. By this definition, the set of natural numbers and the set of square numbers have the same cardinality. They are both countably infinite. Galileo's paradox isn't a true contradiction, rather, it's a demonstration that infinite sets have properties that are deeply counterintuitive. Russell's Paradox. This is a deep and mind-bending paradox that shook the very foundations of mathematics in the early 20th century. It was discovered by the philosopher and mathematician Bertrand Russell. To understand it, let's think about sets. A set is just a collection of things. Some sets contain themselves as a member. For example, you could imagine a set of all things that are not teacups. That set, being a concept and not a teacup, would be a member of itself. Now, let's divide all sets into two categories. The first category is normal sets, which are sets that do not contain themselves as a member. For example, the set of all teacups is not itself a teacup, so it's a normal set. Most sets we think of are normal. The second category is sets that do contain themselves as a member. Here's where the paradox comes in. Russell asked us to consider a new set, which we'll call R. R is defined as the set of all normal sets. In other words, R is the set of all sets that do not contain themselves. Now, Russell asked a simple question: is R a member of itself? Let's try to answer that. Option 1, R is a member of itself. If this is true, then R must satisfy the condition for being in R. The condition for being in R is that a set must not contain itself. So, if R contains itself, then it must not contain itself. That's a contradiction. Okay, let's try option 2, R is not a member of itself. If this is true, then R is a set that does not contain itself. That means R is a normal set. But remember, R is defined as the set of all normal sets. So, if R is a normal set, then by its own definition, it must be a member of R. So, if R does not contain itself, then it must contain itself. Another contradiction. We're completely stuck. Both possibilities lead to a logical impossibility. This paradox showed that the way mathematicians were thinking about sets at the time, known as naive set theory, was fundamentally flawed because it allowed for the creation of self-contradictory objects. The discovery of this paradox was a huge crisis for mathematics and led to the development of more rigorous and complex systems of set theory, like Zermelo-Fraenkel set theory, which have rules in place to prevent this kind of self-referential paradox from arising. Buridan's bridge paradox. This is a classic logic puzzle that explores the nature of truth, promises, and self-reference. The story goes like this: the great philosopher Plato is standing at one end of a bridge. At the other end is his student, Socrates. Plato, in a playful but serious mood, makes a declaration: if the next statement you make is true, I will let you cross the bridge. But if the next statement you make is false, I will throw you into the water. Socrates thinks for a moment and then replies with a single statement: you are going to throw me into the water. Now Plato is in a terrible bind. He has to decide if Socrates' statement is true or false. Let's analyze his options. Suppose Socrates' statement is true. That means Plato is going to throw him into the water. But according to Plato's own rule, if Socrates' statement is true, he must let him cross the bridge. So, if the statement is true, Plato must not throw him in the water. This is a contradiction. Now, suppose Socrates' statement is false. That means Plato is not going to throw him into the water. But Plato's rule says that if Socrates' statement is false, he must throw him into the water. So, if the statement is false, Plato must throw him in. This is also a contradiction. Plato is trapped by his own rules. No matter what he does, he will violate his promise. If he lets Socrates cross, he's validating a false statement. If he throws him in, he's punishing a true statement. The paradox arises from the self-referential nature of Socrates' response. His statement is about a future action that is itself determined by the truth of the statement. This puzzle, often attributed to the 14th century philosopher Jean Buridan, is a variation of the liar's paradox. It highlights the difficulties that arise when we try to apply true/false logic to statements that refer to their own consequences. There's no clean resolution within the framework of the puzzle itself. Any action Plato takes will break his initial promise. It's a clever illustration of how easily our logical systems can be tied in knots by self-reference. The arrow paradox. This is another of Zeno of Elea's famous paradoxes of motion, designed to argue that what we perceive as motion is just an illusion. Imagine an arrow in flight. At any single, frozen instant of time, the arrow is in a specific location in space. It occupies a space exactly equal to its own size. In that instant, it is not moving to where it is, because it's already there. And it's not moving to where it isn't, because an instant is a duration of 0, and it has no time to move. So, at any given instant, the arrow is motionless. It is at rest. But if time is just a collection of these instants, and the arrow is motionless at every single instant, how does it ever move from one place to another? If the entire flight of the arrow is made up of moments of not moving, how is movement possible at all? This is Zeno's arrow paradox. It challenges the very idea of how motion occurs over time. Of course, we know from our own experience that arrows do fly. So, what's wrong with Zeno's logic? The problem lies in Zeno's conception of time and motion. He's treating time as if it's a series of static snapshots, like frames in a film. He's also assuming that at any given instant, the state of an object can only be described by its position, not its velocity. The modern resolution to this paradox comes from the development of calculus by Isaac Newton and Gottfried Leibniz. Calculus gives us a way to talk about instantaneous rates of change, or velocity. In this framework, even at a single instant, the arrow can have a non-zero velocity. Motion is not just about being in different places at different times, it's about having a property, velocity, at every moment. The arrow's motion at an instant is defined by its velocity at that instant, which describes its tendency to be at a different position in the next instant. Zeno's paradox was brilliant because it highlighted the deep conceptual problems in understanding motion without the right mathematical tools. By showing the flaws in a simplistic view of time and space, he spurred future thinkers to develop a more sophisticated and accurate understanding of the physical world. The Prisoner's Dilemma, Paradox of Cooperation. Imagine two criminals, partners in crime, who have been arrested and are being held in separate interrogation rooms. The police don't have enough evidence to convict them on the main charge, only on a lesser charge that carries a 1-year sentence. They offer each prisoner a deal, and the prisoners cannot communicate with each other. Here's the deal offered to each one: if you betray your partner and testify against them, and your partner stays silent, you will go free, and your partner will get a 3-year sentence. If you both betray each other, you will both get a 2-year sentence. If you both stay silent, you will both get the lesser 1-year sentence. Let's look at this from the perspective of one prisoner. He doesn't know what his partner will do. He thinks, if my partner stays silent, my best move is to betray him. That way, I go free instead of getting 1 year. If my partner betrays me, my best move is still to betray him. That way, I get 2 years instead of 3. So, no matter what his partner does, his individual best interest is to betray. The other prisoner, being equally rational, comes to the exact same conclusion. So, they both decide to betray each other, and they both end up with a 2-year sentence. Here is the paradox: by each pursuing their own self-interest, they end up with a worse outcome than if they had both cooperated and stayed silent. If they had both stayed silent, they would have only served 1 year each. This is the prisoner's dilemma. It's a fundamental problem in game theory that shows why two completely rational individuals might not cooperate, even when it appears that it is in their best interests to do so. The dilemma is that the collectively rational outcome, cooperation, is unstable because each individual has a selfish incentive to deviate from it. This simple scenario has huge implications for understanding a wide range of real-world situations, from arms races between countries and price wars between companies to environmental issues like climate change. In all these cases, the paradox highlights the tension between individual and collective rationality and the difficulty of achieving cooperation in the absence of trust and communication. The Paradox of the Ravens, Hempel's Paradox. This paradox, which we've encountered before, is worth revisiting for its subtlety. It explores what counts as evidence for a scientific hypothesis. Let's take the statement, all ravens are black. We can test this by going out and looking for ravens. Every time we find a black raven, our confidence in the statement goes up. If we find a single green raven, the statement is proven false. Now, consider the logically equivalent statement: everything that is not black is not a raven. If the first statement is true, this second one must also be true, and vice versa. They are two ways of saying the same thing. Because they are logically equivalent, any evidence that confirms the second statement should also confirm the first one. This is where the paradox comes in. Let's look around the room. I see a white coffee mug. This mug is not black, and it is not a raven. Therefore, it is a confirming instance of the statement everything that is not black is not a raven. And since that statement is the same as, all ravens are black, observing a white coffee mug should, logically, increase my confidence that all ravens are black. This seems absurd. How can an observation of something indoors, that has nothing to do with birds, tell us anything about the color of ravens? This is Hempel's paradox, named after the philosopher Karl Hempel. There are several ways philosophers have tried to resolve this. One popular view is that observing the white mug does provide evidence, but the amount of evidence is incredibly, almost meaninglessly, small. The number of non-black things in the universe is astronomically large. The number of ravens is very small in comparison. Finding a black raven provides a much more significant piece of evidence because it eliminates a much larger proportion of the potential ways the hypothesis could be false. Another view is that the context of the investigation matters. When we are testing a hypothesis about ravens, we are implicitly restricting our investigation to the domain of ravens. The paradox shows us that the relationship between evidence and hypothesis is more complex than it first appears and that our intuitions about what should count as evidence can sometimes be at odds with the strict rules of logic. The paradox of the court, Protagoras versus Euathlus. This is an ancient Greek legal paradox that involves a teacher, a student, and a contract. The famous sophist Protagoras took on a student named Euathlus to teach him law. They made a special arrangement for payment. Euathlus would pay Protagoras the fee for his education only after he had won his very first court case. Euathlus completed his studies, but then he decided not to practice law. He didn't take on any cases, and so, he never won his first case. As a result, he never paid Protagoras. After waiting a reasonable amount of time, the frustrated Protagoras decided to sue Euathlus for the unpaid fees. Now, they are in court, and Protagoras makes his argument to the judge. He says, "Your Honor, the outcome of this case is simple. If I win this case, then by the court's own decree, Euathlus must pay me. If I lose this case, then Euathlus has won his first case. According to our contract, he must then pay me. So, whether I win or lose, Euathlus must pay." It seems like a foolproof argument. But then, Euathlus, having been well trained by Protagoras, stands up to make his own defense. He says, "With all due respect, my teacher is mistaken. If I win this case, then the court has ruled that I do not have to pay. If I lose this case, then I still have not won my first case. According to our contract, I do not have to pay him until I do. So, whether I win or lose, I do not have to pay." The judge is now faced with a complete contradiction. Both arguments seem perfectly logical, yet they lead to opposite conclusions. This is the paradox of the court. It's a brilliant example of a catch-22 situation, where the conditions of a contract come into conflict with the legal process meant to enforce it. The paradox highlights the problems that can arise from self-referential contracts. The condition of payment, winning a case, is dependent on the very legal action, the lawsuit, that is trying to force the payment. There is no simple legal or logical resolution. Ancient sources say the judges were so flummoxed that they threw the case out of court, postponing the decision indefinitely. It's a timeless puzzle about the limits of contracts and logic when they become entangled with each other. The paradox of the tortoise and Achilles. Let's imagine a race between two unlikely competitors, Achilles, the legendary Greek warrior known for his incredible speed, and a slow, humble tortoise. Being a good sport, Achilles gives the tortoise a head start of, say, 100 meters. The race begins, and Achilles starts running. Now, to catch the tortoise, Achilles must first cover the 100 meters that separated them. That seems easy enough. But in the time it takes Achilles to run those 100 meters, the tortoise, being a slow but steady creature, has moved a little bit further ahead, maybe just 10 meters. So, Achilles now has to cover that new 10-meter gap. But in the time it takes Achilles to cover those 10 meters, the tortoise has crawled forward again, a tiny bit more, maybe 1 meter. So now Achilles has to cover that 1 meter. And in the time it takes to cover that meter, the tortoise has moved a little bit more, say 10 centimeters. You can see where this is going. No matter how close Achilles gets to the tortoise, there is always a new, smaller gap that has opened up because the tortoise is always moving. This is the paradox of Achilles and the tortoise, one of several mind-bending puzzles created by the ancient Greek philosopher Zeno of Elea. It seems to logically prove that Achilles can never actually overtake the tortoise. He has to complete an infinite number of smaller and smaller tasks to catch up, and that seems like it should take an infinite amount of time. Of course, our real-world experience tells us this is absurd. A fast runner will always overtake a slow one. The solution to the paradox lies in a concept that wasn't fully understood until the development of calculus, centuries after Zeno. Zeno's argument is clever, but it's based on a flawed intuition about infinity. The key is that while Achilles has to cross an infinite number of gaps, the time it takes him to cross each successive gap also becomes infinitely smaller. An infinite series of decreasing numbers can, in fact, add up to a finite, definite sum. The infinite number of catch-ups will occur in a finite amount of time, allowing Achilles to finally, and inevitably, pass the tortoise. The Grand Hotel Paradox, Hilbert's Hotel. Picture a hotel, but not just any hotel. This is Hilbert's Grand Hotel, and it has an infinite number of rooms. And on this particular night, the hotel is completely full, there's a guest in every single one of the infinite rooms. Now, a new guest arrives and asks for a room. The night manager, a clever mathematician, doesn't turn them away. Instead, he says, "No problem." Here's what he does. He makes an announcement over the hotel's PA system, asking every guest to please move from their current room, room N, to the next room, room N+1. The guest in room 1 moves to room 2. The guest in room 2 moves to room 3. The guest in room 100 moves to room 101, and so on, all the way down the infinite line of rooms. Because there's no last room, everyone has a room to move into. This simple shuffle frees up the first room, room 1, which the manager then gives to the new guest. But the night is young. A little while later, a bus arrives carrying an infinite number of new guests, all needing a room. The hotel is full again. Surely now the manager must turn them away. But again, he says, "I can accommodate you all." This time, his plan is a bit more complex. He asks every current guest to move from their room, room N, to the room with double their number, room 2N. So, the guest in room 1 moves to room 2. The guest in room 2 moves to room 4. The guest in room 3 moves to room 6. This maneuver moves all the current guests into the infinite set of even-numbered rooms. And what does that leave open? All of the infinite odd-numbered rooms, 1, 3, 5, 7, and so on. The manager can now put the infinite new guests from the bus into these newly vacated rooms. This thought experiment, created by the mathematician David Hilbert, isn't a true paradox in the sense of a logical contradiction. Rather, it's a story designed to show how deeply counterintuitive the concept of infinity is. Our brains are wired to think about finite quantities. In the finite world, a full hotel is a full hotel. But in the world of infinity, the rules are different. A full, infinite hotel can always make room for more, demonstrating that infinity is not just a very large number, it's a completely different kind of quantity with its own bizarre and fascinating properties. The paradox of the unexpected exam. Imagine your teacher makes an announcement to the class on Monday morning. There will be a surprise exam on one day this week, from Tuesday to Friday. You will not know which day the exam will be until I hand it out at the start of class. The students, being clever logicians, start to think about this. One of them says, "The exam can't be on Friday." The others ask why. "Well," she explains, "if we get to the end of the day on Thursday and we haven't had the exam yet, we would know for certain that the exam must be on Friday. But the teacher said it would be a surprise. If we know it's coming, it's not a surprise. So, Friday is impossible. The other students agree this makes sense. Having eliminated Friday, they realize that Thursday is now the last possible day for the exam. Another student chimes in, wait a minute. If Friday is out, then if we get to the end of Wednesday without an exam, we'll know it has to be on Thursday. That wouldn't be a surprise either. So Thursday is also impossible. This logic continues to cascade backward. With Friday and Thursday eliminated, Wednesday becomes the last possible day, but that would be expected after Tuesday, so it's out. Then Tuesday becomes the last possible day, but that would be expected after Monday, so it too is impossible. The students conclude, with seemingly flawless logic, that a surprise exam that follows the teacher's rules cannot possibly happen. They relax, confident in their deduction. And then, on Wednesday morning, the teacher walks in and says, take out a piece of paper, it's time for your exam. The students are all completely surprised. The teacher's conditions were met. The exam happened, and it was a surprise. So where did the students' logic go wrong? This paradox, a close cousin of the unexpected hanging paradox, plays with the tricky nature of self-reference and knowledge. The statement, the exam will be a surprise, is a prediction about the student's future mental state. The paradox arises because the students try to use this prediction to make deductions that, in turn, alter their own mental state, creating a dizzying logical loop. The flaw is in the assumption that a statement about a future surprise can be a concrete, unchanging fact that you can use to eliminate possibilities in the present. The paradox of time travel loops. Let's dive back into the weird world of time travel. Imagine you're a brilliant inventor, but you're stuck on one final problem in designing your time machine. One night, an older version of you appears in your lab. This future self hands you a complete set of blueprints and a worn, leather-bound journal, saying, this is everything you need to know. It's all in here. You study the blueprints, follow the instructions in the journal, and successfully build the time machine. Years pass. You travel through time, have many adventures, and meticulously record everything in that same leather journal. Eventually, you become the old inventor who knows your younger self is struggling. You take the blueprints you used and the journal you wrote, and you travel back to that fateful night to give them to your younger self, completing the circle. This leads to a baffling question: where did the information come from? Who actually designed the time machine? You didn't, you just copied the blueprints your future self gave you. But your future self didn't design it either, he was just following the instructions that you, his past self, had written down after building it. The design of the time machine and the knowledge in the journal seem to have no origin. They are caught in a self-contained and self-creating loop, existing without ever having been created. This is the Bootstrap Paradox, a type of causal loop. It gets its name from the impossible idea of pulling yourself up by your own bootstraps. It challenges our most fundamental understanding of cause and effect, which we see as a straight line where a cause is B. In a bootstrap paradox, an effect can also be its own cause. An object or a piece of information can be its own origin story. Science fiction is filled with these loops, from characters being their own ancestors to objects with no point of creation. While it seems logically impossible, some physicists who study the possibility of time travel suggest that such self-consistent loops might be the only way to travel to the past without creating universe-destroying contradictions. In this view, you can't change the past because you were always a part of it, and your actions in the past are what created the very future you came from. The Pinocchio Paradox. We all know the story of Pinocchio, the wooden puppet whose nose grows longer every time he tells a lie. It's a simple, magical rule: his nose grows if, and only if, he makes a statement that is not true. This rule seems straightforward enough, until Pinocchio says a very particular sentence. Imagine Pinocchio declares, "My nose is about to grow." Let's think about what happens next. We have two possibilities. Possibility 1, his nose grows. But the rule says his nose only grows when he tells a lie. If his nose does grow, it means his statement was true. But if he was telling the truth, his nose isn't supposed to grow. This leads to a direct contradiction. So, let's try possibility 2, his nose does not grow. If his nose stays the same length, it means his statement, my nose is about to grow, was false. He lied. But the rule says that if he tells a lie, his nose must grow. This also leads to a direct contradiction. We are completely stuck. If his nose grows, it shouldn't have. If it doesn't grow, it should have. The statement creates a scenario that is physically and logically impossible under the rules of Pinocchio's existence. This is the Pinocchio Paradox, and it's a wonderfully simple and intuitive version of the more famous liar's paradox. It's built on self-reference. The statement Pinocchio makes is about a consequence that is itself determined by the truth or falsity of the statement. This creates an unbreakable loop of contradiction. It's a perfect illustration of how our systems of logic, and even magical rules in a fairy tale, can be brought to a grinding halt by a sentence that cleverly talks about itself. The Cretan Paradox, all Cretans are liars. Let's travel back to ancient Greece, to the very origins of logical puzzles. The story involves a philosopher and poet named Epimenides, who was from the island of Crete. In one of his poems, Epimenides made a now famous declaration, all Cretans are liars. This simple statement creates a perplexing puzzle. We have to ask ourselves, is Epimenides' statement true or false? Let's analyze the options. The crucial piece of information is that Epimenides himself is a Cretan. First, let's assume the statement is true. If it's true that all Cretans are liars, and Epimenides is a Cretan, then he must be a liar. But if he is a liar, then the statements he makes must be false. Therefore, his statement that all Cretans are liars must be false. So, if the statement is true, it logically leads to the conclusion that it must be false. This is a clear contradiction. So, the statement can't be true. Let's try the other option, the statement is false. If the statement, all Cretans are liars, is false, what does that mean? It doesn't mean that all Cretans are truth-tellers. It simply means that at least one Cretan is not a liar, that is, at least one Cretan sometimes tells the truth. Is this a contradiction? Not necessarily. It could be that Epimenides is a liar, making his statement false, and his statement is false precisely because there's some other Cretan on the island, maybe a shepherd named Nikos, who always tells the truth. So, unlike the pure liar's paradox, this statement is false. The Cretan paradox isn't a perfect, inescapable contradiction. It's possible for the statement to be false without creating a logical crisis. However, it's famous because it was one of the first times thinkers grappled with the thorny problems of self-reference and laid the groundwork for centuries of logical puzzles to come. The Moore's Paradox. This is a peculiar paradox that isn't about a logical contradiction, but about the absurdity of saying something that could, technically, be true. Imagine someone walks up to you and says, "It is raining outside, but I do not believe that it is raining." Now, let's think about this. Is it possible for that sentence to describe a real state of affairs? Yes, absolutely. It could be a fact that it is raining outside. And it could also be a fact that this particular person doesn't believe it's raining. Maybe they haven't looked out the window and are just guessing. The external world and a person's internal beliefs can be mismatched. There's no logical contradiction between the two parts of the sentence. The paradox arises in the act of saying it. When a person makes a statement about the world, like, "It is raining," they are implicitly communicating that they believe it to be true. The very act of assertion carries with it an implied belief. So, when the person says, "It is raining, but I do not believe it is raining," they are doing two contradictory things at once. With the first half, they are implying a belief. With the second half, they are explicitly denying that same belief. This is Moore's paradox, named after the philosopher G. E. Moore who first identified it. It highlights the difference between a logical contradiction and what's called a pragmatic or performative contradiction. The statement itself isn't logically impossible, but the act of uttering it is bizarrely self-defeating. It's a puzzle that reveals a deep connection between the language we use, the beliefs we hold, and the way we present ourselves to the world. You can't coherently assert something and deny your belief in it in the same breath. The paradox of free will versus determinism. This is one of the oldest and most profound philosophical puzzles, and it gets to the very heart of what it means to be human. We all have the powerful, intuitive experience of free will. It feels like you are the one in control, making conscious choices. You chose what to eat for breakfast this morning, you're choosing to listen to this right now, and you will choose what to do next. This feeling of being the author of your own actions is fundamental to our sense of self, morality, and responsibility. But then, there's the scientific worldview of determinism. This is the idea that every event in the universe, including the firing of neurons in your brain, is the necessary result of prior causes. The universe operates according to fixed physical laws. If you could know the exact state of every particle in the universe at the moment of the Big Bang and you had a powerful enough computer, you could, in theory, predict everything that would ever happen, including you choosing to eat cereal this morning instead of toast. Here is the paradox: how can these two ideas possibly coexist? If every decision you make is simply the inevitable outcome of a chain of cause and effect that was set in motion billions of years ago, in what sense are you free? Your feeling of choice would be just an illusion, a trick your brain plays on itself. The concepts of free will and determinism seem to be mutually exclusive. If one is true, the other must be false. This has led to a great philosophical debate with a few main camps. The hard determinists accept the scientific picture and conclude that free will is indeed an illusion. The libertarians, not the political kind, argue that we do have genuine free will, and therefore, strict determinism must be false. Perhaps there's some room for true randomness or a special kind of mental causation that operates outside of physical laws. And then there are the compatibilists, who try to argue that the paradox is a false one. They suggest that free will and determinism can coexist if we define free will differently. For a compatibilist, free will isn't the ability to violate the laws of physics, but simply the ability to act according to your own desires and intentions, without being coerced. As long as your actions are caused by your own internal mental states, you are free, even if those mental states were themselves predetermined. There is no easy answer, and it remains one of the great unresolved questions of philosophy. The infinite monkey paradox. This is a famous thought experiment that beautifully illustrates the mind-boggling nature of infinity. The idea is this: if you place a monkey in front of a typewriter and let it hit the keys randomly for an infinite amount of time, it will, with a probability of almost 100%, eventually type out the complete works of William Shakespeare. Our immediate intuition screams that this is impossible. The odds of typing even a single coherent sentence by chance are astronomically low, let alone the entire play Hamlet. The number of possible combinations of letters is so vast that it feels like it could never happen, even with all the time in the universe. And that's where our intuition fails us, because we're not talking about a very long time, we're talking about an infinite time. The key to the paradox, which is more of a mathematical theorem than a true paradox, is that the probability of typing any given letter is not zero. It might be tiny, but it exists. And in the realm of probability theory, any event with a non-zero probability, no matter how small, will almost surely happen if you give it an infinite number of opportunities. Think of it on a smaller scale. If you're rolling a standard six-sided die, what are the odds of rolling a 6? It's 1 in 6. What if you wanted to roll a 6 100 times in a row? The odds are incredibly low, but they are not zero. If you roll that die for an infinite amount of time, you are virtually guaranteed to eventually hit a streak of 100 sixes. The infinite monkey theorem simply scales this logic up. The sequence of letters in Hamlet is just a very, very long target sequence. Over an infinite timeline, every possible sequence of keystrokes will eventually appear. The paradox isn't a contradiction in logic, it's a clash between the sheer scale of infinity and the limits of our human imagination. The twin paradox, relativity. Let's explore one of the most famous consequences of Albert Einstein's theory of special relativity. Imagine two identical twins, Alice and Bob. Alice stays on Earth, while Bob becomes an astronaut. He gets into a futuristic spaceship that can travel at nearly the speed of light and sets off on a journey to a distant star. After reaching the star, he turns around and comes back to Earth. According to Einstein's theory, one of the bizarre effects of moving very fast is something called time dilation. This means that for a moving observer, time itself passes more slowly relative to a stationary observer. So, from Alice's perspective on Earth, as she watches her brother's ship zip through space, the clock on his ship is ticking much more slowly than her clock on Earth. When Bob's ship finally lands back on Earth after his long journey, the twins meet, and they make a shocking discovery. Alice has aged significantly, say 50 years. But Bob, for whom time was passing much more slowly, has only aged a few years. He is now dramatically younger than his own twin sister. This effect, as strange as it sounds, is a real and experimentally verified consequence of relativity. But here is the apparent paradox. Motion is relative, isn't it? From Bob's perspective in the spaceship, it was the Earth that was moving away from him at incredible speed and then coming back. So, shouldn't Bob see Alice's clock as the one that was running slow? Shouldn't Alice be the younger one when they reunite? Why is there a difference? The resolution lies in the fact that the twin situations are not symmetrical. Alice, on Earth, remained in a single, consistent frame of reference. Bob, on the other hand, did not. In order to travel to a star and return, he had to accelerate to a high speed, decelerate to stop, turn around, accelerate again, and finally decelerate to land back on Earth. This acceleration is the key. It breaks the symmetry between the two twins. The twin who undergoes acceleration is the one who unambiguously experiences the time dilation effect. There is a real, physical difference in their journeys, and that is why Bob is the one who returns to find he is younger than the twin he left behind. The paradox of Schrödinger's cat. Imagine a cat. Now, imagine putting this cat inside a completely sealed, soundproof box. You can't see, hear, or know anything about what's happening inside. Also inside this box is a strange and deadly device. It consists of a tiny amount of a radioactive substance. This substance is so small that in the course of 1 hour, there is an exact 50/50th chance that just one of its atoms will decay. If an atom decays, it triggers a Geiger counter, which in turn releases a hammer that smashes a vial of poison gas, instantly killing the cat. If no atom decays, the poison is not released, and the cat remains alive. The box is sealed, and an hour goes by. Now, before you open the box, what is the state of the cat? Our common sense tells us the answer is simple: the cat is either alive or it's dead. We just don't know which one until we look. But this is where the strange and paradoxical world of quantum mechanics steps in. According to the standard interpretation of quantum mechanics, the radioactive atom, until it's observed, is not in a definite state. It's in a superposition of both states at once. It has both decayed and not decayed simultaneously. And because the fate of the cat is directly linked to the state of the atom, the cat itself is also in a superposition. Before the box is opened, the cat is both 100% alive and 100% dead at the same time. It exists in a blurry, probabilistic reality, a ghostly mix of both possibilities. It is only when you open the box and make an observation that reality is forced to choose one of the two outcomes. The act of looking, of measuring, collapses the superposition into a single, definite state, either a living cat or a dead cat. This is the famous thought experiment of Schrödinger's cat, proposed by the physicist Erwin Schrödinger in 1935. It wasn't meant to be a real experiment, but rather a way to show how bizarre and counterintuitive the rules of the quantum world become when you try to apply them to large, everyday objects. The paradox lies in the clash between what quantum math seems to describe, a cat being simultaneously alive and dead, and what we know to be true from our everyday experience, which is that cats are one or the other, never both. It highlights the deep and still unresolved mystery of where the quantum world ends and the classical world of our experience begins. The paradox of Maxwell's demon. Let's think about one of the most fundamental laws of the universe, the second law of thermodynamics. In simple terms, this law states that in any isolated system, entropy, or disorder, always increases. Hot things cool down, organized systems become messy, and energy tends to spread out and become less useful. You can't unscramble an egg, and a cup of lukewarm coffee will never spontaneously separate into a hot layer and a cold layer. But in 1867, the physicist James Clerk Maxwell came up with a clever thought experiment that seemed to challenge this unbreakable law. Imagine a box filled with gas at a uniform temperature. This gas is made up of countless tiny molecules, some moving faster, hotter, and some moving slower, cooler. Now, we divide this box into two chambers with a tiny, massless door in the middle. And we hire a microscopic, intelligent being, a demon, to operate this door. The demon's job is to watch the molecules as they fly around. Whenever it sees a fast-moving, hot molecule heading towards the right chamber, it quickly opens the door to let it through. And whenever it sees a slow-moving, cold molecule heading towards the left chamber, it also lets it pass. It keeps the door shut for any slow molecules trying to go right or fast molecules trying to go left. Over time, what happens? The demon, with its intelligent sorting, has separated the molecules. The right chamber becomes filled with fast-moving, hot molecules, while the left chamber becomes filled with slow-moving, cold molecules. The demon has taken a system at a uniform temperature and, without doing any apparent work, created a temperature difference. It has decreased the entropy of the system, seemingly violating the second law of thermodynamics. You could even use this temperature difference to run an engine. This is Maxwell's demon paradox. For over a century, it puzzled physicists. How could this little creature defy a fundamental law of nature? The resolution came with the development of information theory. The key insight is that the demon is not a passive observer. To do its job, the demon needs to gather information, it needs to measure the speed of the molecules. The act of acquiring and storing this information has a cost. The demon's brain, or its little notepad, has to record the data, and this process of storing and eventually erasing information itself creates entropy. Modern analysis has shown that the amount of entropy created by the demon's information processing will always be greater than or equal to the decrease in entropy it achieves by sorting the gas. The second law is safe after all, but the paradox was incredibly useful in helping scientists understand the deep physical connection between energy, entropy, and information. The paradox of Loschmidt's reversibility. Let's consider the laws of physics that govern the world at a microscopic level, the laws of classical and quantum mechanics. One of the most fundamental properties of these laws is that they are time-reversible. This means that if you were to watch a video of two particles colliding and bouncing off each other, and then you played that video in reverse, the reversed version would also look perfectly plausible. It would obey all the same physical laws. There's no inherent arrow of time in the fundamental equations of physics. Now, let's contrast this with the world we experience every day, which is governed by the second law of thermodynamics. This law tells us that time has a very definite direction. Entropy, or disorder, always increases. An egg falls and smashes on the floor, but we never see the smashed egg reassemble itself and fly back up. A drop of ink spreads out in a glass of water, but we never see the diffused ink gather itself back into a perfect droplet. The universe moves from order to disorder. Here is the paradox, first raised by the 19th century physicist Johann Loschmidt. How can the time-irreversible behavior of the macroscopic world emerge from the perfectly time-reversible laws that govern its microscopic components? If you could perfectly reverse the velocity of every single particle in a gas that has just expanded, the laws of physics say that it should retrace its path and go back into its corner, a process that would involve a massive decrease in entropy. So why does this never happen in reality? This is Loschmidt's reversibility paradox. It highlights a deep tension between the microscopic laws of physics and the macroscopic arrow of time. The modern resolution to this paradox is based on probability and initial conditions. While it is physically possible for all the particles to spontaneously move back into a small corner of the box, the number of ways they can be arranged in a disordered, spread-out state is astronomically, incomprehensibly larger than the number of ways they can be arranged in an ordered state. So, while any single microscopic process is reversible, the overwhelming statistical probability is that the system will evolve towards a state of higher entropy simply because there are vastly more of those states available. The reason we see eggs break and not unbreak is because the unbreaking state, while physically possible according to the reversible laws, would require an initial arrangement of particles so fantastically improbable that we would never expect to see it in the entire history of the universe. The Paradox of Banach, Tarski. Prepare for a paradox that seems to break our most basic intuitions about geometry and physical objects. It comes from a branch of pure mathematics, so it's not something you can do in your kitchen, but it is logically and mathematically sound. Imagine you have a solid, three-dimensional sphere, like a billiard ball. The Banach-Tarski theorem states that it is possible to cut this sphere into a finite number of pieces. The original paper used 5, and then, without any stretching, bending, or adding new material, you can reassemble those pieces to create two identical spheres, each one the exact same size as the original. Let that sink in. You take one ball, you cut it up, and you reassemble the pieces to get two balls. This sounds like magic. It violates our deepest sense of conservation of volume. How can you double an object just by rearranging its parts? This is the Banach-Tarski paradox. It's not a logical contradiction, but a mathematically proven theorem that is wildly counterintuitive. The key to how this is possible lies in the nature of the pieces you cut the sphere into. These are not the kind of simple, solid pieces you could cut with a knife. They are infinitely complex, fractal-like sets of points with no well-defined volume. They are what mathematicians call non-measurable sets. To construct these bizarre pieces, the proof relies on a controversial mathematical principle called the axiom of choice. This axiom allows mathematicians to select elements from an infinite number of sets, even if there's no rule for how to make the selection. Using this axiom, it's possible to carve up the infinite points of the sphere in such a clever and pathological way that when you rearrange them, the notion of volume no longer applies. The points that make up the pieces are so scattered and intermingled that they can be rotated and shifted to fill the space of two spheres. The Banach-Tarski paradox is a profound result in modern mathematics. It shows us that our everyday, intuitive concepts of length, area, and volume don't always apply in the abstract world of infinite sets. It doesn't mean you can actually duplicate gold balls in the real world, because physical objects are made of atoms and can't be cut into these infinitely complex, point-based sets. But it does serve as a powerful reminder that the world of pure mathematics can be a much stranger and more wonderful place than our physical intuition would have us believe. The Paradox of the Omniscient Book. Imagine there is a special book in a library. This book is a complete and true record of your entire life. It describes every event, past, present, and future, with perfect accuracy. One day, you find this book. You open it and start to read about your past, and you find that everything it says is correct. You then turn to the present chapter, and it accurately describes you sitting in the library, reading the book. Now, you turn to the next page, which describes your future. You read the sentence, "After reading this page, you will stand up and walk out of the library." You are now in a very strange position. You have a choice. You can either stand up and walk out, thereby fulfilling the book's prophecy, or you can choose to remain seated, just to prove the book wrong. Herein lies the paradox. Let's say you decide to defy the book and stay in your chair. If you do this, then the book's prediction that you would walk out is now false. But the book was defined at the very beginning as being a complete and true record of your life. Its statements cannot be false. This leads to a contradiction. Okay, so maybe that means you don't have a choice. Maybe your free will is an illusion, and you are compelled to follow what the book says. You must stand up and walk out. But if you do that, was it really a choice? If you only did it because the book said you would, it feels like you've lost your freedom. The very act of reading the prediction seems to have taken away your ability to choose otherwise. This is the paradox of the omniscient book, and it's a classic puzzle about the conflict between omniscience, knowing everything, and free will. It's a variation on the broader theme of fatalism and determinism. The paradox arises because the knowledge of the future becomes a part of the present, influencing the very events it predicts. The information itself becomes a causal factor. There are a few ways philosophers try to resolve this. Some argue that such a book is a logical impossibility from the start. Others suggest that the moment you read the book, the future it describes is a future without you having read it, and your act of reading creates a new timeline. Still others might argue that this simply proves that free will, in the sense of being able to do otherwise, is an illusion. Whatever the case, it's a powerful thought experiment that forces us to question the relationship between knowing the future and our ability to create it. The Paradox of Knowledge, Meno's Paradox. In one of Plato's famous dialogues, his mentor Socrates is having a conversation with a young nobleman named Meno. They are trying to figure out the definition of virtue. After a few failed attempts, Meno becomes frustrated and presents Socrates with a clever and tricky puzzle about the very nature of inquiry and knowledge. Meno's paradox, as it's now known, goes something like this: how can you search for something if you don't know what it is? If you have absolutely no idea what you're looking for, you won't be able to recognize it even if you stumble right upon it. And if you already know what you're looking for, then there's no need to search for it in the first place, because you already have the knowledge. So, according to Meno, inquiry is either impossible or pointless. You either don't know what you're looking for, in which case the search is futile, or you do know, in which case the search is unnecessary. This seems to put a stop to all learning and discovery. This is the paradox of knowledge. It's a fundamental challenge to the process of learning. Socrates recognized it as a clever debater's trick, but also a serious philosophical problem. His proposed solution is a fascinating one. He suggests the idea of anamnesis, which is the theory that our souls are immortal and already possess all knowledge from a previous existence. Learning, in this view, is not the acquisition of new information, but the process of recollection, of remembering the knowledge that is already latent within us. He demonstrates this by guiding an uneducated slave boy through a complex geometry problem, showing that the boy can arrive at the correct answers simply by being asked the right questions, thus recollecting his innate knowledge. While we may not subscribe to the idea of immortal souls and past lives today, the paradox still has relevance. A more modern way of looking at it is to say that it rests on a false dilemma. It assumes that knowledge is an all-or-nothing affair. You either know something completely or you don't know it at all. In reality, we often have partial knowledge. We might know some properties of what we're looking for, or have a rough idea or a hypothesis that guides our search. The process of inquiry is about moving from a state of partial or vague knowledge to a state of more complete and certain knowledge. Meno's paradox is a great starting point for thinking about what it really means to know something and how we move from ignorance to understanding. The Catch-22 Paradox. The term, Catch-22, has entered our everyday language to describe a no-win situation, a paradoxical problem where the only solution is denied by a rule or circumstance inherent in the problem itself. It comes from the brilliant 1961 satirical novel of the same name by Joseph Heller. In the novel, set on a U.S. bomber base during World War II, the main character is a pilot named Yassarian who wants to stop flying dangerous combat missions. There is a military rule, Catch-22, that says a pilot can be grounded if they are declared insane. So, Yassarian goes to the flight surgeon and claims he's insane. Why? Because he's afraid of being killed on the bombing runs. And here is the catch. The doctor explains to him that a concern for one's own safety in the face of real and immediate danger is the process of a rational mind. Anyone who wants to get out of combat duty isn't really crazy. So, the very act of asking to be grounded proves that you are sane, and therefore, you are fit to fly. On the other hand, if a pilot was actually crazy, he wouldn't be able to see that he was crazy and wouldn't ask to be grounded, so the system would never identify him. The paradox is inescapable. The only way to be grounded is to be insane, but if you're sane enough to ask, you're not insane. If you fly the missions, you're crazy, but if you say you're crazy, you're sane. It's a closed loop of bureaucratic logic designed to ensure that no one can ever actually escape their duty. Catch-22 is a powerful literary device, but it also describes a very real type of paradox that occurs in rules and systems. It's a situation where someone needs something that they can only get by not needing it. For example, you can't get a job without experience, but you can't get experience without a job. Or you need to borrow money to prove you're financially responsible, but you can only get a loan if you're already financially responsible. The paradox highlights the absurdity and the circular reasoning that can often be embedded in bureaucratic or social systems, creating a trap from which there is no logical escape. The paradox of Newcomb's problem. Imagine a being with superior intelligence, let's call it Omega. Omega has an incredible ability. It can predict your choices with almost perfect accuracy. One day, Omega presents you with a game. In front of you are two boxes, Box A and Box B. Box A is transparent, and you can see that it contains $1,000. Box B is opaque, you can't see what's inside. Omega tells you that you have two choices. Choice 1, you can take both boxes. Choice 2, you can take only Box B. Now, here's the crucial part. Omega explains how the game was set up yesterday. Omega made a prediction about what you would choose. If Omega predicted that you would choose only Box B, it placed $1 million inside Box B. If Omega predicted that you would take both boxes, it put nothing in Box B. You are standing in front of the boxes. The money is already in there, or it isn't. Omega has already made its prediction and left. The question is, what should you do? This is Newcomb's problem, and it creates a fierce debate between two different schools of rational thought. The first line of reasoning, often associated with causal decision theory, says you should take both boxes. The argument is simple, the money is either in Box B or it's not. That decision was made yesterday. Your choice right now cannot change what's in the box. So, whatever the state of Box B, you will always be $1,000 richer by taking both boxes. If Box B is empty, you get $1,000 instead of $0. If Box B has the million, you get $1,001,000 instead of just the million. It seems foolish to leave a guaranteed $1,000 on the table. But the second line of reasoning, associated with evidential decision theory, says you should take only Box B. The argument here is that you have overwhelming evidence that Omega has predicted your choice correctly. People who choose both boxes almost always walk away with only $1,000. People who choose only Box B almost always walk away with $1 million. Your choice is strong evidence for what prediction Omega made. So, if you want to be a millionaire, you should perform the action that is characteristic of millionaires in this game, take only Box B. The paradox pits two principles of rationality against each other. Do you choose the option that seems causally dominant, or the option that has the highest expected utility based on the evidence? It's a deep philosophical problem with no universally accepted answer, and it forces us to think about the nature of free will, determinism, and what it truly means to make a rational choice. The paradox of the unexpected lottery. This paradox is a fascinating blend of probability and logic that can seem to prove that a lottery can never be won. Let's imagine a lottery that will be held every day for the next 100 days. There is a rule, there will be exactly one winner, and the day of the win will be a surprise. The winner will not be able to deduce in advance that today is the day. Now, let's try to reason about this from the perspective of a ticket holder on the first day. They start thinking about the last possible day, day 100. They reason, the lottery can't be on day 100. If we get through 99 days with no winner, we would know for certain that the win must happen on day 100. But the rules say the win must be a surprise. Knowing its coming would violate the surprise rule. Therefore, day 100 is an impossible day for the lottery. Having logically eliminated day 100, they then consider day 99. Well, since day 100 is out, day 99 is now the last possible day. So, if we get through 98 days with no winner, we would know that the win must be on day 99. This would also not be a surprise. So, day 99 is also impossible. You can see where this is going. This backward induction continues, eliminating day 98, then 97, all the way back to the very first day. The conclusion seems to be that a surprise lottery, as defined by the rules, can never happen on any of the 100 days. But then, on day 23, the winning numbers are drawn, and someone wins. They are completely surprised. The rules of the lottery, that there would be one winner and it would be a surprise, were perfectly fulfilled. So, what went wrong with the seemingly airtight logical proof that the lottery was impossible? This is the paradox of the unexpected lottery, and it is almost identical in structure to the unexpected hanging and unexpected exam paradoxes. The flaw in the logic is subtle. It lies in using a future condition, the need for a surprise, to make deductions about the present. The reasoning, if we get to day 99, we will know, is a hypothetical. The statement that the lottery will be a surprise cannot be used as an axiom to prove that certain days are impossible, because the very truth of that axiom depends on the lottery actually being a surprise. The paradox teaches us that human knowledge and expectation are slippery concepts that don't always behave like the neat, clean axioms of a formal logic proof. The paradox of self-reference. The paradox of self-reference isn't a single paradox, but rather a whole family of puzzles that arise when a statement, an idea, or a system refers to itself. It's a fundamental concept that has caused headaches for logicians, mathematicians, and philosophers for thousands of years. The simplest and most famous example is the liar's paradox. Consider the sentence, "This statement is false." Let's try to figure out if it's true or false. If the statement is true, then what it says must be true. It says that it is false. So, if it's true, it must be false. That's a contradiction. Okay, so let's assume the statement is false. If it's false, then what it says is untrue. It says it's false, so if that's untrue, the statement must be true. So, if it's false, it must be true. Another contradiction. We are trapped in an endless loop of impossibility. This is the core of self-referential paradoxes. They create a situation where a system tries to talk about its own properties in a way that leads to a logical meltdown. We've seen this theme in many other paradoxes. The Barber Paradox, the barber who shaves all men who don't shave themselves, is about a self-referential rule. Russell's Paradox, the set of all sets that do not contain themselves, exposed a self-referential problem at the heart of mathematics. Even paradoxes like the unexpected hanging rely on a self-referential condition about the prisoner's own knowledge. The discovery of these paradoxes has been incredibly important. They're not just clever word games, they reveal the inherent limits of formal systems of logic and language. Thinkers like Kurt Gödel used ideas from self-reference to prove his famous incompleteness theorems, which showed that any sufficiently powerful mathematical system will contain true statements that it cannot prove. The general approach to handling these paradoxes is to create rules that forbid or restrict certain kinds of self-reference. For example, some logicians propose a hierarchy of languages, where a statement in one language can only talk about the truth of statements in a lower-level language, but never its own. The paradox of self-reference shows us that while our ability to think and talk about ourselves is a powerful feature of consciousness and language, it's also a path that can lead directly into the deepest and most fascinating logical abysses.